have some edge between the edges. Sorry, there is an edge between the two vertices. Yeah. So you can see that the color of the vertices are different if the vertices are neighbors. Yeah, if there is an edge between two vertices. So that's the definition of actually the vertex coloring. Okay, for millennial people, you can see this logo, this Google Chrome logo. Yeah, if you use graph coloring, yeah, to represent this logo by ignoring the white color, you can have actually a complete graph with four vertices, and because all are adjacent, yeah, then they must be used different colors. Yeah, so you can find here that this logo have ignoring, by ignoring the white color, you can have four colors. What if we include the white one, the white color? So that's the homework, but I think it is simple. Yeah. Okay, now we start with the variation of graph coloring. The first one is vertex coloring. I took the definition in Ringel and Hartsfield's book, which is I think very popular books, yeah, in graph theory. Given a graph G, vertex coloring of G is defined as assignment color to the vertices of G such that no two adjacent vertices receive the same color. Yeah. The objective is we use the minimum numbers of color. Yeah. So we define chromatic number of graph denoted by Kg is the minimum number of color necessary to color the vertices of G. Yeah. Kg equal to K means that the graph G is colorable by K colors, but G is not colorable by K minus 1 colors. Yeah. Another version of definition is we can find it in Hammett in 2017. Given integer K, a K coloring of graph is assignment of K colors to the vertices of G so that each vertex get one of the K colors. So in this case, we don't care if the vertices are neighbors or are adjacent or not. We just give any color to the vertices. Yeah, but now we have some restriction. A coloring of graph is said to be a proper coloring if no two adjacent vertices have the same color. Now we can find the same definition as the previous slide. Yeah. Also, the chromatic number of graph G is denoted by Kg is the smallest integer K for which the graph has a proper coloring. This is an example. We can use the previous slide because it's easier to understand. First, we can, in the first graph, we can color any vertices of graph by any color. We don't care anything about adjacent vertices. Yeah, we call it tree coloring. Yeah, but by definition, this coloring is not proper. Why? Because there is two adjacent vertices have the same colors. Yeah, you can see here the two adjacent vertices have yellow colors. The next thing is we call it for coloring. So this coloring is proper. Yeah, you can see if there are no adjacent vertices have the same color. All adjacent vertices have different colors. Yeah, but this is not optimal. Yeah, because we can have a better coloring, a better proper coloring, which only use two colors. Yeah, this one. So you can see here that we can only use, we can use two colors to color this graph. Yeah, it's meant that the chromatic number of this graph is 2. Yeah. Can we use one colors? I think it's impossible because there are at least 2 adjacent vertices. In this case, we have to use 2 colors. Okay. The first graph, which is easy to prove, is the complete graph. The chromatic number of complete graph is n, because every vertices in complete graph is adjacent to each other. So we cannot have n minus 1 colors. Yeah, so that's why the smallest number of colors has to be n. Okay. The second one, this is the example of complete graph. We can see this complete graph on 5 vertices have 5 colors. Yeah. Okay. The next graph is complete bipartite graph. Complete bipartite graph has chromatic number equal to 2. Yeah. Because in complete bipartite graph, we can partition the vertices into independent sets. So we can color the first set by red color and the second set by blue color. Yeah. Okay. In fact, any bipartite graph has at least one edge has chromatic number 2. Yeah. I mean, if we have a bipartite graph, we always have the chromatic number equal to 2. Okay, this is the example. You can see, I think it is easy to see. This is the first partition, and this is the second partition. Okay, 3. For 3, because 3 can be drawn as a bipartite graph, then the chromatic number of 3 is equal to 2. Yeah. So the way we color the vertices of 3 is as follows. We can consider one vertex as a root, yeah, this vertex, and then we can just draw the 3 layer by layer, I mean level by level, yeah, according to the distance of vertices to the root. Yeah, if the distance of vertices to the root is odd, then we color by blue. If the distance between that vertices to a root is even, then we can color by red, the same color as the root. So we can keep going until the what's called the last level of the tree. Yeah. Okay, so we can see that the color of, the chromatic number of 3 is 2. Okay, the last thing is cycle. Yeah, the chromatic number of cycle with n vertices, where n is greater or equal to 3, is 2 when n is even, and 3 when n is odd. So I think it is simple to prove that. Yeah, you can just give alternative color to that the vertices of the cycle. For even is easier. Yeah, so we can have like a pair between blue and red color. But for the even case, for the odd case, we will have problem in the last vertex. Yeah. Because when the last vertex is colored by blue, for example, and we will meet the, if the last vertex colored by blue, then it will have the same color with the previous one. If it is colored by red, it will have the same color by the next vertex. Yeah, so it has to be use the third color. We call it yellow color. Okay, this wheel, yeah, wheel is simple. We can give one vertex in the middle of the cycle, in the center of the cycle, and connect every vertices of cycle. So that's why the chromatic number of wheel is equal to the number, the chromatic number of cycle plus 1. Yeah. Okay, this is the example. Okay, this is the lower bound for the chromatic number. If G is subgraph of G, then the chromatic number of H is less than or equal to the chromatic number of G. What does it mean? It means that if we want to see the chromatic number of G, we can see the lower bound, yeah, by checking the chromatic number of the subgraph. Yeah, so it's you can find that a lower bound, and then to see the upper bound, then we can have this. This other. Before I give you an upper bound, let me give an example for the lower bound. You can see here that this graph have a click, yeah, on n and on 4 vertices, which means that we can have a complete graph on 4 vertices here, K4. It's meant that the lower bound of the this graph, yeah, the chromatic of this graph, at least 4. Yeah, so you can try color by this the vertices of this graph by 4 colors, but if you cannot give 4 color for this graph, then you can have another color, yeah, another like this one. Yeah, you can see here. In fact, we don't have we cannot have 4 colors here. Sorry, here is 4 color. Here is also 4 color, but for this one, we cannot have the same color as one of the vertices and click 4. Yeah, so the chromatic number of this graph is 5. Yeah. Okay, for the upper bound, we can have a very famous theorem, Brooke theorem. Yeah, suppose G connected graph that is neither a complete graph or odd cycle. If the largest if the largest vertex degree of G is big delta, then the upper bound of the chromatic number of G is big delta. So we have this one. Yeah. Okay. Now you can see at home, or you can work this graph or color this graph. Yeah. And find the chromatic number of this graph. The upper bound, we can use the largest degree of the graph, and the lower bound, you can use the chromatic number of the subgraph. Yeah, if the upper bound is equal to the lower bound, then that's the chromatic number of the graph. Yeah. Okay. The next variation of graph is graph coloring is edge coloring. Yeah, the definition of edge coloring, yeah, can found in Ringel and Hartsfield book again. Yeah, given a graph G, edge coloring of G is assignment color to the edge of G such that no two adjacent edges receive the same color. So the objective is also the same. We want to minimize the number of color. Yeah, and we have edge chromatic number denoted by chi prime of G is the minimum number of color necessary to color the edge of G. Yeah, chi prime G equal to K means the graph G is edge colorable by K color, but G is not edge colorable by K minus 1 color. Okay. In Wimmer 2014, they give some version of the definition. Given an integer K kh coloring of G is a labeling F, yeah, to h of G by 1 to up to k, yeah. And an edge coloring of G is said to be proper if no two adjacent edges have the same color. Yeah. So edge chromatic number of G is the smallest integer k for which the graph has a proper k edge coloring. Actually, this the similar definition with the Vertex coloring. So this is the example. You can see here that any adjacent edges cannot have the same color. So in this part, we have the same color. So this one is not proper, but we can use 3 colors. Yeah. In this one, it is proper, but we have to use 4 colors here. In the last graph, we have proper and minimal, yeah, 3 coloring. Okay. Okay, the lower bound for edge chromatic number is actually equal to the largest, equal to or greater to the largest Vertex degree of G. Yeah, if the largest Vertex degree of G is big delta, then the lower bound of the edge chromatic number is equal to big delta. Yeah, so you can easily prove that. You can imagine that if this is an edge and this is the largest, sorry, a vertex with the largest degree, then the number of edges, suppose this one is the big delta, yeah. So you can see the number of edges incident to the vertex is equal to big delta, then they must be have the different color. So the color must be at least big delta. Okay, the upper bound is giving, I think this one is also very famous, yeah, Fishing and Gupta, yeah. Suppose G be a graph. If the largest vertex degree of G is big delta, then the upper bound of the edge chromatic number of G is equal to big delta plus 1. It means that actually the edge chromatic number of G is in between big delta and big delta plus 1. Yeah. Okay, this still from Fishing. Yeah, the edge chromatic number of K regular graph is either K or K plus 1. Yeah, this is the example. Yeah, if it is complete graph with even order, then the chromatic number of the complete graph is equal to the degree, yeah, to the degree of complete graph, which is if a complete graph is K to N, then the edge chromatic number of K to N is 2N minus 1. If it is odd, yeah, then the number of edge chromatic number of K to N minus 1 is 2N minus 1, which is actually the degree plus 1. Yeah. Okay, this is the bipartite graph. For bipartite graph, with the largest vertex degree big delta, then the edge chromatic number is equal to big delta. Okay, another variation of graph coloring is phase and map coloring, which is I give already in the beginning of this slide. List coloring, path coloring, total coloring, equitable vertex coloring, circular vertex coloring, acyclic vertex coloring, star vertex coloring, which is actually the same as circular vertex coloring, yeah, and circular edge coloring, and also acyclic edge coloring. Okay, and some people actually derive graph coloring using graph labeling. So I give you some definition for this derivation of graph coloring. Yeah, you call it local anti-magic coloring. There are also some variation of local anti-magic coloring. Yeah, actually, graph theories are very creative. So if we have one problem, then many problem will come. Yeah. So the first one is local anti-magic vertex coloring. The second one is local anti-magic total vertex coloring. And the third one, super local anti-magic total vertex coloring. And then the fourth one, or the last one, is local anti-magic edge coloring. But in this this one, we still have any derivation for this one. We call it local anti-magic total edge coloring, and also super local anti-magic total edge coloring. Okay, let's see. This problem first introduced by Arumugam and others, yeah, and his student Premalata, and also we know Martin Baca very well, and also Andrea Simanikova Venovikova, yeah. In 2017, the local anti-magic on graph labeling on graph G with V vertices and A edges is defined to be assignment F to E by 1 to up to the number of edges, so that the weights of any two adjacent vertices U and V are distinct. That is, the weights of U not equal to the weights of V. Okay, where the weights of U is calculated by the sum of the edge label incident to U. Okay, and this one. Okay, sorry. Yeah, the set of edge incident to U. Of course, you can see that because any two adjacent vertices of U, I mean the weights, yeah, the weights of any two adjacent vertices U and V are distinct. It means that actually any local anti-magic labeling induce a proper vertex coloring. Okay, so that's why if you want to find the color of graph, especially vertex coloring, then we can use this labeling. Yeah. Okay. The local anti-magic chromatic number, denoted by KLAG, is the minimum number of colors taken over all coloring induced by local anti-magic labeling of G, which means that actually this, the same as the minimum number of different weights, yeah, of that labeling. Okay. For any graph G, KLA of G is greater or equal to KG. Yeah, I think it is simple because, of course, the classic chromatic number, I mean the original chromatic number will be the lower bound of this local anti-magic chromatic number. Okay, but you can see that the differences between KLAG minus KG will be arbitrarily large. Yeah, sometimes is equal to 0, but sometimes is equal to the large number. Yeah, you can see it's depend on the kind of graph. Yeah, the family of graph. Yeah. Okay, this is the example. Yeah, you can see that even you can see that when we talk about vertex coloring, the chromatic number is equal to 2. But when we use the local anti-magic coloring or local anti-magic labeling, the chromatic number of local anti-magic will be equal to 3. Yeah. Okay, this is another version. Yeah, we call local vertex anti-magic total labeling, and the definition is similar with the previous one, but instead we label all component of graph, not just the edges, but also the vertices. So that's why the function or the map now is going from the union of vertex set and the edge set to the number of 1, 2, up to the number of vertices and the number of edges. Yeah, otherwise similar. Yeah, of course, this kind of labeling is also induce a proper vertex coloring of G. Yeah, and the color of U will be assigned by the weights of U. And we also have this chromatic number thing. Yeah, and we have also the lower bound. Yeah, which is the original chromatic number of G. Yeah, but what happened if you compare between chi-lat of G and chi-LAG? Yeah, of course, this one is smaller because we can have some combination for that number to be the labeling, yeah, of the vertices and the edge of graph. Okay, this is the example. Now you can see that this local anti-magic total vertex coloring have chromatic number equal to 2, which is the same as the original one. Yeah. Okay. The next one we call it super. Super means if the vertices, yeah, if the vertices of G receive the smallest label, yeah, this one is also induce a proper vertex coloring, and we have super local anti-magic total chromatic number denoted by chi-slat, yeah, of G, and this is the minimum number of color taken over all coloring induced by super local anti-magic total coloring of G. And we have this relationship, yeah, so chi-slat G must be greater or equal to what's called chi-lat G, and also greater or equal to chi-LAG, and also is greater or equal to chi-G, or chromatic number of G. Okay, this is the example. We still have the same chromatic number, yeah, and this one is local edge anti-magic labeling or anti-magic edge coloring. Yeah, instead of we label the edges, now we label the vertices. Yeah, so the map will be goes from V to the number of 1, 2, up to the number of vertices. Yeah, and the weights of any adjacent edge, yeah, have to be distinct. So actually, this is the same as the definition of edge coloring. So that's why any local edge anti-magic labeling induce a proper edge coloring of G. Yeah, and we also have the anti-magic edge chromatic number. Okay, and we have the relationship here. Of course, edge chromatic number of local anti-magic must be greater or equal to the edge chromatic number of G. Yeah. Okay, this is the example. It's actually similar to the for the cycle, similar to the edge coloring, vertex coloring. Yeah, but you can see here that the chromatic number is equal to 3, which is larger than the original edge chromatic number. Yeah. Okay, and we also have another version. We call it total. Yeah, and this one is defined or introduced by Jember Mafia. Yeah, Bu Ika, Pak Dafe, Prof. Dafe, and their student. I think, no. This is our last previous lecture. Yeah, Pak Hasan. Yeah, we can see here that instead we only label the vertices, we also label the vertices. Yeah, so that's why the map is going from 1 to up to the number of vertices and the number of edges. Yeah. Otherwise, the same definition. Yeah. Okay. This is the super version. Yeah. So if we label the vertices by the smallest label, then we call it super local edge anti-magic total labeling. Okay. This is I can summarize the local anti-magic coloring. Yeah, you can see here that for local anti-magic, we label the edges and we calculate the weights on vertices. Yeah, for local anti-magic total, we label both vertex and edge, and we calculate the weights on vertex. Sorry. Okay, you can see this one, the what's called the I think this one, yeah, quite wrong. Okay, the second version is super local edge anti-magic. Yeah, we label, sorry, I think we label this one by vertex, not this one. Okay, sorry. And we calculate the weights on edges. Yeah, and the second one for the edge version is called local edge anti-magic. Total, we label both and we calculate on edges. Yeah. Okay. Next, this is the result, summary of the result on that kind of labeling. Yeah. There are still many open problems, especially for the super version. Yeah. And the next, the revision is called local distant irregular coloring. Yeah, which is quite different definition. Local distant irregular total labeling of graph G with a vertex set V is an assignment F to V from V to the set of number 1 to up to K, so that the weights of two adjacent vertices are distinct. And the only differences is how to count the weights. Yeah, the weights is on vertex X is defined as the sum of the label of all vertices adjacent to X. So this is the formula. Yeah, and we have the local irregular chromatic number of G. Yeah, we call Kailis G. Yeah, is the minimum of cardinality local irregular vertex coloring. This definition is given by Arika, Bu Arika. Yeah, it's also Jember Mafia, I think. And this is the example. Yeah, you can see that we label, the number inside the circle is the weights. Yeah, inside the vertices is the weight, and this is the label. So we label all by one. And you can see that the weights of two adjacent vertices are distinct. Yeah. Okay. Now the application. So the last part of my talk, the application of graph coloring. Okay. The first one is in chemical storage. Yeah. The problem is when we want to store n different chemical, yeah, the condition is if there is interaction between some pair of the chemical, yeah, in some part of in some type of chemical, if it is a mix between them, it will explosive. Yeah. So the question is, what is the smallest required number of compartment in the storage? Yeah, to store the n different chemical. So we can have, we can solve the problem by using graph coloring. Actually, we can define the graph G with vertex set V and edge set E. Yeah, vertex V, yeah, correspond to the chemical. And edge UV, if there is interaction between chemical U and V, cause the explosive. so it means there is an edge between them. Yeah. So the number of the independent set of vertices implies of a compartment. So the number of compartment actually is the chromatic number, yeah, especially the smallest number. So you can see that the number of compartment is related to the number of smallest color used to the vertex coloring. Yeah, can you imagine? Okay, the second problem is Sudoku, Sudoku puzzle. Yeah, you can put integer number from 1 to 9 to the grid. Yeah, usually 9 times 9 grid, yeah, with a digit, so that each column, each row, and each of subgrid that compose the grid contain all the digit from 1 to 9 are different. I mean, in the same one number has to appear once in each row, each column, and in subgrid, yeah, like this. Okay, so you can represent this Sudoku puzzle into vertex coloring of graph. So if you see here, you can see that there will be 81 vertices of the graph. It is crowded. Yeah, so that's the solution. Sudoku can be thought of a graph with 81 vertices. Yeah, one vertex for each cell and two vertices are connected by an edge if they cannot be assigned in the same value. Okay, all cells in the same row, column, or block mean subgrid, yeah, 3 times 3, will have edge between their corresponding vertices. So the optimal solution in the case of the Sudoku puzzle is to find a coloring using only 9 colors. Yeah, I'm not sure whether it is easier for you to directly fill the integer to the Sudoku, or you find the color first and then find the Sudoku puzzle. You know, in bahasa, saya nggak tahu apakah lebih mudah langsung mengisi puzzle-nya, Sudoku-nya, atau lebih mudah mewarnai grafnya. Kalau orang graf, saya yakin lebih mudah mewarnai grafnya. Tapi bagi orang non-graf, mungkin lebih mudah langsung mewarnai, mengisi Sudoku-nya, ya, Sudoku puzzle-nya. Okay. This is for the case for time 4 Sudoku puzzle. Even for time 4, you can see the graph representation. Yeah, yeah, you can fill the remaining cell here. We already have 1 here, 3 here, and 2 here, and 4 here. Either you fill this grid with numbers from 1 to 4, or color this graph by using 4 colors. Yeah, it's up to you. Okay, the third application is when we want to minimize the exam period. Yeah, how to schedule exam in minimum parallel session where no two concurrent exam have a common student. Yeah. First, we define a graph with vertex set V and edge set E. And then you can see that vertex V corresponds to the course, and edge UV if course U and V have a common student. So an independent set of V vertices imply the parallel exam season. It means that the chromatic number of G is actually the smallest number of the parallel session. Ya, so jika Bapak Ibu yang terutama guru ingin membuat jadwal kuliah atau jadwal pelajaran, bisa menggunakan pewarnaan graf ya untuk memudahkan atau untuk mengoptimasi jumlah waktu yang dibutuhkan ya. Okay. Actually, this is our research. We use the coloring, especially the local anti-magic labeling of graph, to what's called to assign an expatriate during their stay in Jember. Yeah, expatriate mean a person who live outside his or her native country and is physically mobile across international border, whether professional or personal reason, whether for short or long period of time, whether organizationally sponsored or not, and regardless as to whether one is crossing an ocean or moving across land. So this is the in economics, yeah. An expatriate assignment at brand company in other country must be optimized due to the short-term duty, yeah, because the salary of the expatriate usually is very high, yeah, I mean, very good, yeah. And accuracy calculation is needed to optimize the expatriate assignment, including its schooling system. So it's meant that we have to optimize their time during their stay in Jember. Usually they work in the industrial company, yeah. I mean in what's called agro industry in Jember, yeah. Okay, this is the solution. Actually, this is similar to the exam schedule, yeah. We define a graph G with a vertex at V and edge at E. Vertex V correspond to the assignment, and edge UV if assignment U and V have common expatriate. So the independent set of vertices implies a parallel assignment session. So we use this chromatic number as the smallest number of parallel assignment session. Yeah, we usually give some case. Yeah, a company have 5 expatriate, for example. Yeah, say E, B, C, D, and E. These 5 expatriate assigned to 5 tasks. AB, yeah, AC in the same division, yeah, AC in the same division, and BAD in the same division, and this one, and so on. Yeah. Okay. One day, each task has to execute it for 1 hour. Obviously, all 5 expatriates cannot execute during the same hour because some expatriates have to do several tasks and cannot be in 2 places at the same time. The question is, what is the number of hours needed for all of the expatriates to do their tasks? So we draw the condition of the expatriate with this graph. Yeah, you can see here that this group of expatriates have an age between them. If there is 1 or more expatriate in common here. We have A here and we have A here, so that's why there is an age between them. And there is B here and also there is A here, so that's why there is an edge between them, and so on. Now we color the vertices of graph using the classic coloring, yeah, vertex coloring, and we can see here we have the minimum color must be equal to 3. So the chromatic number is equal to 3. Yeah, it's mean that this expatriate assignment time schedule can be represented as in this table. Sorry. Yeah, you can see here. See this the schedule. So I think it's easier for us, yeah, to make a scheduled system. Okay. The last thing that we did is a watering plan in the what's called in the field. Yeah. So in the processes of watering, it is done as much as 2 times as in the day. Yeah. This treatment is carried out even to all existing plants, although the frequency of watering each plant is different. So some plants need once a day, some plants need 2 or twice a day. Watering frequency, a number of car will be used a data parameter in determining the schedule of watering plan. What we want to say here, it's actually we try to make some application, scheduling system application, when we want to water plant in the field, Okay, this is the data for that one. We have agriculture in our university, agriculture field, parks, park, and we simulate if we plan to water the plant in that park using what's called electric cars, actually, and we have this one, for the representation of the relationship between cars and plant. I mean that car one, because of the access, some route probably is very narrow, some are very what's called large. So car one only can have access to plant 1, for example, and plant 2, plant 3, plant 4, and plant 7. And car 2 can access can water plant 1, plant 3, and plant 6, and so on. So in this case we use edge coloring. We use edge coloring for this part. You can see here, if see the blue color here, mean that in the same time car one can water T1, plant 1, and car 2 can water this one, the plant 3, and car 3 can water plant 4. So in this, sorry, not this one. This is red. This is blue. This one. So for the next time, the second time, you can choose the red color. Mean that M1 to T1, T2, M2 to T1, M3 to T4, and so on. We make some application, actually, some information system, which is done by our student, and I think it's worked very well using edge coloring. Okay, I think that's all for my talks. Thank you very much for your attention, and I give back this session to the chair. Thanks, Obi.
Okay, thank you very much, Professor Slamin. Very nice presentation about graph coloring, variation, derivation, and application. Okay, now we go on to the discussion time. For participants who have a question, you can write it in the chat box, or you can ask to the Professor Slamin directly by unmute your microphone. Okay, any question?
No question. Probably it is clear, or it is not clear at all.
I think it is clear, Professor Slamin. Okay, Professor Slamin, there is a question from Mrs. Kiki. Is there any open problem for us?
Of course. Thanks, Bu Kiki. Terima kasih, Bu Kiki. Of course, there are many open problems. The first one, actually, we still have many problems in some application. I think many people from other field, from other mathematics, like especially in information system, keep asking how to solve this problem using graph coloring and so on. But in graph theory topic, especially the one which is still open is when we talk about local irregular distance labeling. We still have many. I'm not updating, yeah, but someone works, especially I think Ibu Diari student in University of Brawijaya work on this problem as well. Local irregular distance labeling. After Ibu Arika from Jember introduced that, there are actually some particular gap is already done, yeah, but many other family of graph, especially if you use some operation, which is still open, yeah, and some of them use inclusive, and some of them is use not inclusive. I mean, if we include the level of vertices calculated in the weights, ya. Begitu Bu Kiki.
Okay, Bu Kiki, how is the answer? Is that enough, or do you still have any other question? Okay. Thank you very much, Professor Slamin. Is there any other question from another participant?
How about this one? Oh, okay. No more question, I think.
No more question? Okay, because there is no question, I think your presentation was very clear, Professor Slamin, and all of the participants here have already understood about your presentation. Thank you very much, Professor Slamin. Before we go on to our third invited speakers, I will read the summary of Mr. Slamin talks about graph coloring, variation, derivation, and application. Graph coloring is one of the most popular topics in the graph theory with some variation, derivation, and application. Given an integer k, a k coloring of a graph is an assignment of k colors to the sum element, vertex, edge, face, or their combination of graph G, so that each element gets one of the k color. A coloring of a graph is said to be a proper coloring if no two adjacent elements have the same color. The chromatic number of graph G, denoted by chi G, is the smallest integer k for which the graph has a proper k coloring. Okay, thank you very much for Professor Slamin. Terima kasih. Please give a big virtual applause for Professor Slamin. Thank you very much.
Terima kasih Obi, terima kasih Bapak Ibu semua.
Thank you.
Thanks all.
Okay, now we go on to our third speakers. The third presentation will be delivered by the chairman of ICCGANT Research Group, Professor Davik, MSc, PhD. Okay, hello, how are you, Professor Davik?
Yeah, how are you, Obi? Thanks.
I'm fine.
Good afternoon.
Okay, thank you. You are the co-host now. You can use the share screen. While waiting for Professor Davik presentation, I will read the short CV of Professor Davik. Professor Davik, MSc, PhD, is a lecturer in the Department of Postgraduate Mathematics Education, Faculty of Teacher Training and Education, University of Jember. He is a professor on combinatorics and combinatorial education. He completed his master in University of Manchester, UK, and he got the PhD degree in the University of Ballarat. Now, he is the Dean of Faculty of Teacher Training and Education and the Chairman of ICCGANT Research Group. He has 179 documents in the Scopus with the H index 12. He is awarded a Sinta Award Best 50 Researcher in Indonesia and the Best Researcher in the University of Jember. For Professor David, floor is yours.
Thank you, Obi. Assalamualaikum warahmatullahi wabarakatuh. Let me share my slide presentation. The title of my talks today is Rainbow Anti-Magic Coloring of Graph. It is joint work with Ika S.T. Agustin, Rido Alvarisi, Susanto, and Venkata Chalam from India, as well as Brian Septori. Before I present my slide, I again say sorry to all of you. At last year, we have conference, international conference in face-to-face format in this building. And today we have a new building in the left side. Last time in the right side that you have a parallel session. We finished the both sides of the building. So this is the new look of the University of Jember. So hopefully next year, the COVID-19 outbreaks has been over, and then we will have international conference again in face-to-face format. And currently, our university has 15 faculties and 30,000 students. And in each faculty, we have a lot of research group, and either in the departmental level, as well as in the faculty level, and even also we have a research group in the university level as a Center of Excellence of the University of Jember. ICCGANT is a part of the Center of Excellence, as ICCCGANT is a research group in the university level. And now currently we organized the 4th International Conference. And from yesterday, we invited 6 presenters in a plenary speaker, as a plenary speaker. Now I'm the last presenters for the last session of this conference. As we mentioned, this is international conference on combinatorics. So I also say sorry to the audience, since there are a lot of topics delivered by invited speaker, more in combinatorics. But yesterday, we already presented the invited speaker talking on what applied mathematics, modeling, and optimization. Now, the graph session. Graph could be in fundamental science or basic sciences, mathematical sciences perspective. Combinatoric or graph could be in mathematics education. But right now, I will talk about the graph in mathematical sciences. As we know, there are a lot of motivations already introduced by graph scientists to give more a strength research of graph theory, the scientists not only working on the fundamental research, that we have exploration research, also we have innovation research, as well as we have a diffusion research. Diffusion research is the taking the result research into a social life. Professor Slamin already mentions how the application of graph labeling, graph coloring, as well as also graph in degree diameter, for example, into a real life. Now, we try to find out application of graph labeling into a crypto system, which is there are two keys in crypto system. It is encryption key and decryption key. What do we mean? What do we know by crypto system? Crypto system is a system which convert a plain text to ciphertext, or ciphertext to plain text by the application of encryption and decryption algorithm. And the strength of crypto system rely on the management key. So actually finding or obtaining the encryption key is a very important thing in the crypto system. The keys should be managed such that it is hard for any intruder to analyze the key. That's the concept of crypto system. So the main issue how to develop a modern or a secure modern crypto system such that the key between plaintext and ciphertext is hidden. So actually the two things in crypto system is encryption process and decryption process. Encryption process transform plain text into ciphertext, and then we need a key system. And then again, how to reveal the ciphertext such that the human being can read it. So this is again the process of decryption, ciphertext to plaintext, that we need a key system. So the recycle from plaintext, ciphertext, and ciphertext to plaintext, this is actually the process of a crypto system. There are a lot of technique from the conventional one to the modern one, and by means of the anti-magic labeling, by means of the other concept of labelings, we can implement the concept into a crypto system. This is an example which already published by Prihandoko and me, and also Ibu Ika, in International Journal of Combinatorics, Indonesian Journal of Combinatorics. The title is Anti-Magic Total Graph the Super H Anti-Magic Total Graph on establishing a stream cipher. So when we have a graph, a label graph, here from the graph that we can see a cycle of order 6, and then we'll assign a label onto vertices, and then we have the addition of the two adjacent vertices, and then we will have edge weight. And then if we consider the all edge weight are different, then it is anti-matching. By means of this kind of labels, and then we try to have encryption process by using the formula y I equal xi plus ki modulo 26. Why it is modulo 26? Because it is the representation of the alphabetic Roman alphabetics, because from A to YZ we count from 0, 1, 2, 3 until 25, and then we have a modulo 26. So again, by decryption process, and then we just have the inverse of the linear equation, yi equal xi plus ki modulo 26. So what is the detail of this kind of crypto system? Actually, this one, firstly, we call Affine chipper, and then by using this graph, the anti-magic labeling, with using polyalphabetic crypto system, and then finally we have this kind of example. For example, consider A, B, C, D, E, F, G, H, I, G, K, L, M until Z, and then we try to put assignment for A is start from 0, B is 1, C is 2 until Z is 25. Of course, completely we have a modulo 26. For example, we have FKIP UNEJ as a plain text. And then how to store this one, for example, in the computer storage, and simply saying that how to transform into a ciphertext. Just simply we use the previous graph, label graph, and we have a cost F is xi, ki, this is the affine chipper, and this is the formula. Xi is the number, the ordered number of F in from the alphabetic order, A, B, C, D, E, F. F is 5, because we count starting from 0, and then we have I. What is key I? Key I is from the label of the cycle of graph, of cycle sequence. 1 here, this is the label of the vertices in the top layer. If we have a cycle of order 6, of course, enough for constructing the ciphertext from the plain text FKIP. Okay, continue. Of course, xi plus ki is 6. And finally, we have I as 6. And the ciphertext for 6, after F, we have G is a 6. And then we have G as the replacement of F in the ciphertext. And finally, we have all FKIP, UNEJ. Then we have this kind of ciphertext. So FKIP UNEJ now read by GMRPH, CHRI. Of course, it is very hard to read for a human being unless we transform again into a plain text by means of encryption and decryption process, and by means of the graph labeling. Then we will read it. We can read that ciphertext again, because it is already in plain text. So this is the motivation. So there are a lot of from conventional application that already mentioned as well by Prof. Slamin, and now we have this kind of thing. and then you can read this application in Indonesian Journal of Combinatorics. Now we just flashback into the very old fashion of labeling, because we have been researching a lot about this kind of study. Started from 2007 when I was studying in the University of Ballarat, currently the Federation University. But before that, you can see a lot of researchers working on that. And then you can see the dynamic survey of Joseph Gallian about the graph labeling. So this is the one that we have done so far, and many researchers already solved the open problem, and many researchers already done the some specific family as well as general family, and also obtain the upper bound and lower bound and everything. Even they already characterized for the general graph. So this is the anti-magic labeling. So I believe people already know about this kind of definition. But I just give an example, for example. So if we have a cycle, for example, how to assign label, in such way we have an anti-magic Vertex labeling, H labeling, sorry, an anti-magic H labeling, because the evaluation on every H. So we just assign a label into these vertices, yeah. Sorry, moderator, could you give me 3 minutes? I have a problem. Yeah, just a minute. A technical problem.
Okay, it's okay, Professor David.
Yes.
Okay, while waiting for Professor David, I think we can check the question. There is a question for Joe, maybe. Joe?
Yeah, I can now.
Oh, okay.
Could
you can
I,
continue,
yeah.
Professor David. Thank you.
Yeah. Now, okay, just a problem. Hopefully this one. Okay. So when we have old fashion of anti-magic labeling, then we have this one, 5, 6, 7, 4, 5, 6, 7, 8. It is considered consecutive. So that's why this one is a type of the anti-magic labeling. If only the H label are different, the H weight are different, then we consider it is anti-magic. But if it is consecutive, or if it's form an arithmetic sequence, and then we call AD anti-magic label. Okay, this one, the technique. And then we have a lot of expansion of anti-magic labeling of graph. We have H anti-magic Vertex labeling. So the evaluation of which done for every H. As well as we have a Vertex H anti-magic Vertex anti-magic age labeling, the evaluation of label on both vertex or age, and evaluation of age done for every vertex. And we have also just a minute. I have again a problem. Yeah, sorry, I am not sure. I don't know why it is a lot of problem. Okay, now this one, now we have here again, this is the extension of even in the age weight, we also have some evaluation. Yeah, type of evaluation. The first one is just age anti-magic, and then total if we include the age as well, and if we have the at least 3 vertices, and then we have a cover. Yeah. Now, the second definitions, this is the new notion of, in our research, combining anti-magic labeling and rainbow coloring. But previously we have a rainbow coloring definition, and rainbow coloring is already interesting study in graph theory. There are a lot of people, and there is a dynamic survey also. Su Liang Li as well written a book about dynamic survey of rainbow coloring. We have this kind of definition. Rainbow coloring is an age coloring. C, yeah, maps the element of age into 1, 2, 3 until K, where adjacent age might be colored the same. A part is colored a rainbow path if no 2 edges are colored the same. An age color graph is said to be a rainbow connected if 2 distinct vertices are connected rainbow path. And age coloring of G, which admit a rainbow connected, is colored a rainbow coloring. I believe it is easy to find for path. It is simpler and trivially we can find the rainbow coloring. And rainbow coloring is not a proper coloring like just proper coloring normally. So every 2 adjacent edges could be having the same color. But in a proper coloring, all the adjacent 2 adjacent vertices or 2 adjacent edges must have a different color. But in rainbow, we can have 2 color to the same color. This is a part, yeah, and this is a for bipartite graph. There are 2 colors of edges. And the rainbow connection number, of course, 2. And this one is a fan graph. We have 3 colors. And of course, the rainbow connection number is 3. And we have a book graph. So I believe in graph theory study, there are people already working on that a lot, and maybe the open problems already done by some researcher, and now they leave the very hardest problem. It will be very complex, and it considered is non-polynomial time, even it is NP hard problem. Now, from these two notions, the first one is anti-magic, the second one is rainbow. We try to find out a new notion. And normally we have, this is the extension of rainbow connection. Of course, we have H rainbow K connection, strong H rainbow K connection, Vertex rainbow K connection, strong Vertex rainbow K connection, total rainbow K connection, and strong rainbow K connection. Okay, with these two notions, I have already a book with the super H anti-magic, total labeling, and the rainbow connection of graph, and then we combine now. We have a rainbow anti-magic color. This is that actually the concept of recent study that our research group members working a lot on this. So what is the strategy of developing the definition of rainbow anti-magic coloring? The first one is take definition from H anti-magic labeling. And the second one, take the definition of H rainbow connection and combine the two notions of any H anti-magic labeling and induce a rainbow coloring of G if every H is assigned by the color, assign the color with the weight of the anti-magic labeling. So the rainbow anti-magic connection number of graph denoted by RECG is the smallest number of K color required to H color the graph with which UV such that the graph is a rainbow connected. So I try to develop the formal definition with kind of this in the following. So maybe you can read it. Let GV be a connected, undirected, and simple graph with vertex, set V, and its set for a bijection F map from a vertex element into 1, 2, 3 until the number of vertices and the associated weight of H weight under F is the weight of H is F U plus FV is the assignments of the vertex of the two adjacent vertices. The bijection F is called an anti-magic vertex labeling if the H weight are distinct. So this is the definition. Let me give you an example. If you have this one, yeah. So of course, we first start assigning the labels from the vertices. And then finally, we have this one. This is anti-magic labeling. If we consider the H weight are different, and then we have anti-magic labeling. And then how to have a rainbow anti-magic labeling? Then look at the H weight of every H. So we do not necessarily have an H weight are all distinct. For example, in this case, we have 4, we have 6, 6, 7, 7. But it is a rainbow because when we start from every vertex to other vertex, and then we will have a rainbow path. What is the rainbow path? If exists any distinct color on the any path from vertex to other certain vertex. So the rainbow path is not necessary for all paths in the 2 vertices. If we have only one path assigns a rainbow color, then we consider this is a anti-magic rainbow coloring. Normally, if we have a anti-magic coloring, rainbow coloring, we do not assign a label on the vertices. But for rainbow anti-magic coloring, we start assigning a label in the vertices. Look at that one. The path is different. That's a rainbow. For example, again here. Yeah. It is also an anti-magic rainbow coloring. Because we start assigning label on the vertices according to anti-magic labeling definition. And then we have an edge weight, and we consider the edge weight as assignment for the rainbow coloring. So not necessary to have all edge weights are distinct. For the researcher, for the potential research expansion for the rainbow anti-magic, in the future, we can have a strong rainbow anti-magic coloring. So what do we mean by strong rainbow anti-magic coloring? If you can find a short part, the shortest part, consider to rainbow part. If you have a vertex rainbow anti-magic coloring, then we consider the evaluation of the edge of the vertex width on every vertex. And the potential, again, another research expansion on rainbow anti-magic coloring is a strong vertex rainbow anti-magic color. And the other one is rainbow anti-magic K connection. So this is the future research for a rainbow anti-magic color. I have been trying to have a paper about this rainbow anti-magic coloring. The first one is try to have trying to study on the specific graph, of course. This is normally that we have done. Then the second one, we try to characterize for the operation of graph. For example, there are 2 graphs and a certain operation, for example, coronation of graph and the other operation, and start for having a characterization for the 2 graphs in that operation as well. And normally, again, for having a good manuscript or good paper, we try to have a lower bound of this study. In this study, we have a rainbow anti-magic coloring, and then we have the lower bound of the rainbow anti-magic coloring is a rainbow coloring. So for any connected graph G, then rainbow anti-magic coloring of G greater than equal rainbow coloring. And we develop a theorems. Let G be any connected graph. Let RCG and delta G be the rainbow connection number of G and the maximum degree of G respectively. Then rainbow anti-magic coloring of G greater than equal maximum of rainbow connection G and delta G. And we also have another theorem for any connected graph G. And let F be a bijection from Phi to the set 1 to Phi. Let UV be two vertices of G. If the degree of UV is 1 until 2, then there exists a rainbow path. This is another general thing of our study. And for the specific one, we have this kind of rainbow anti-magic connection. And finally, we have a lot of generalization as well. And hopefully, these manuscripts can be done in the short future. So this is for the illustration of the result of the rainbow anti-magic rainbow anti-magic label. It is not considered total yet because we only assign the label on the vertices. So if we assign the label on the edges as well, and the edge weight consider the addition of the two vertices, two adjacent vertices, including one edge, then we consider this is the total rainbow anti-magic, the rainbow anti-magic total level. So this one for the star that we have, and this one for a cycle. That's we have a theorem before, and this is for the wheels. We have that one, and this is the way how to prove the theorems. I believe for the simple family of graph, for example, path and everything, it is simple to prove. But for the complex thing, I believe we need to give more effort to prove it. And this is the hopefully this one is done in the short future. We have our own rainbow anti-magic coloring of graph. It is a new notion that we couldn't find any publication before, unless we have a publication, a lot publication on anti-magic labeling, a lot publication on rainbow coloring. But for a rainbow anti-magic coloring, we have one student working on that, one PhD student working on rainbow anti-magic coloring of graph. Now he's studying in the University of Airlangga, Surabaya. Yeah. And finally, I should conclude our presentation by proposing this open problem. The first open problem, of course, normally people starting study a certain notion or study of graph, we start from finding the upper bound or lower bound. Now we have a open problem one, determine the upper bound of a rainbow anti-magic connection number for any connected graph. This one, of course, very hard to solve. The second one, continue to obtain the exact value of rainbow anti-magic connection number of some special graph and their operations, and characterize the exact value for any graphs. And the open problem 3, obtain the construction technique for rainbow anti-magic coloring derived from anti-magic labeling. So I believe construction technique is very important when we establish the construction for a certain notion of study. For example, in here, a rainbow anti-magic coloring, then we can use the construction to any graph. So this one actually very hard and challenging study in graph theory. So that's all from me. And then maybe we can discuss if anyone interesting to have study and to do research on a rainbow, anti-magic coloring, then you are more than welcome to join with our research group member. Thank you very much. Sorry for a little bit problem because my connection is a bit poor. And thank you again for your attention. And I give it back to moderator.
Okay, thank you very much, Professor Davik, for a very interesting talk about rainbow anti-magic coloring of graphs. Okay, for participants who have a question, you can write it in the chat box, or you can ask it directly to Professor Davik by unmute your microphone. Okay, any question? No question? Okay, Professor Davik, I think your presentation was very clear, and all of the participants here have already understood about your presentation. I would like to say thank you very much for Professor Davik, but I will read the summary of the Professor Davik talks about rainbow anti-magic coloring of graphs. A graph G is a rainbow anti-magic if G has a rainbow anti-magic labeling. A path P is a vertex label graph G is said to be a rainbow path if for every two edges UV, U prime, V prime element of edges P satisfy WF UV not equal to WF U prime V prime. If for any two vertices U and V of G there is a rainbow UV path, then F is called a rainbow anti-magic labeling of G. The rainbow anti-magic connection number of G denoted by RACG is the smallest number of colors taken over all rainbow coloring induced by rainbow anti-magic labeling of G. Okay, please give a virtual big applause for Professor Davik, MSc, PhD. Thank you very much, Professor Davik.
Yeah, thank you very much, Obi. Thank you very much for everyone. Again,
thank you.
I'm very impressed with all your attendance or your presence in this conference, and hopefully after this we can have a joint research, especially on my talk and my study, rainbow anti-magic labeling. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, ladies and gentlemen, we still have one question from Mr. Fawaz for Joe. Hello, Joe. Do you still with
hi.
us? Okay.
I have answered that question, I believe, from Fawaz.
Okay.
The answer was yes, Kn is the only graph with n-1.
Okay, thank you very much, Joe, for the answer. The answer is yes. Okay, I think we come to the end of the second day of plenary session of ICCGANT 2020. I would like to say thank you very much for all of the invited speakers. Terima kasih banyak Joe, Associate Professor Joe Ryan. Thank you very much Professor Slamin. Thank you very much Professor Davik for an informative and interesting presentation. Hopefully all of us can get a new knowledge and it can help us to create a good paper that can be published in the international reputable journal. From the keynote speaker's talk, there are some open problems. Hopefully after this international conference, we can solve it and make some joint research. And then after that, hopefully our work can be published in the international reputable journal. I think that's all from me. I am Robiatul Adawiyah, together with my friend Rafiantika Megahnia Prihandini, would like to ask for your apologies if there is any mistake during this plenary session. Akhirul kalam, wabillahi taufiq wal hidayah, wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, I will give it back to the master of ceremony. Thank you very much.
So that is the end of the plenary session. We are going to have 45 minutes break before the parallel session. The parallel session will be start at 12:30 Western Indonesia time.
Acara selanjutnya adalah Isoma selama 45 menit dan kita akan melanjutkan parallel session pada pukul 12.30 waktu Indonesia Barat. Terima kasih.
See you, Joe. Goodbye.
Bye, Slamin.
Bye. Okay. Keep healthy, okay? Stay healthy.
You too.
Thank you.
Ada suaranya, Pak.
Thank you Pak David. Panitia, terima kasih semuanya. Thank you.
Cek.
Langsung kan kayak kemana? Ladies and gentlemen, welcome back to the 4th ICCGANT 2020. We are going to have parallel session, and these are the following rules. First, all participants should use their full name, while presenters should use their paper ID underscores full name. For example, 001 underscores Rosanita. Second, participants should accept the breakout request from the host by clicking Allow button. Third, participants should turn off the audio when it is unnecessary. Fourth, participants should not leave the meeting until the parallel sessions end. Fifth, the certificate will be given only if the participant joined the Zoom meeting in the first and second day of ICCGANT plenary session. Sixth, the presenter that seven, further information and further question and information, please contact our host by clicking Ask for Help button. The parallel session will also be the end of all of our agenda. The end of the parallel session will be closed by each of the room host.
Acara selanjutnya adalah parallel session, namun sebelum itu perlu kami informasikan terkait tata aturan dalam sesi paralel ICCGANT 2020 melalui Zoom Meetings. Di antaranya yang pertama adalah peserta dimohon untuk menulis nama lengkap dan untuk presenter dimohon untuk membubuhkan nomor paper ID di depan nama dengan contoh 001 garis bawah Rosanita. Kedua, peserta dimohon untuk menerima permintaan breakout dari panitia dengan cara mengklik kata allow. Ketiga, peserta dimohon untuk menonaktifkan audio ketika tidak digunakan. Peserta dimohon untuk tidak meninggalkan Zoom meeting hingga acara parallel session berakhir. Sertifikat akan diberikan dengan syarat peserta wajib mengikuti Zoom meeting hari pertama dan kedua ICCGANT plenary session. Apabila ada pertanyaan lebih lanjut, dimohon untuk klik tombol Ask for Help dan akan terhubung dengan host kami. Acara ini akan ditutup oleh host di masing-masing room dan saya, Frenza Virus Firmansyah dan rekan saya,
Sri Ulana Wangsari.
Selaku pembawa acara, mohon maaf atas kekurangan dan kesalahan dalam serangkaian acara ini. Sampai jumpa dalam acara ICCGANT berikutnya. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Astagfirullahaladzim. 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 Ya Allah, astagfirullahaladzim. Kakak ngomong-ngomong. Nggak dimatiin, kadang bisa jadi MC-nya tuh iniin otomatis nunda Zoom kan. Nggak, tadi kakak matiin, cuma misalnya tiba lagi ngomong itu jadi moodnya otomatis, kalau nggak jaringannya suara